Okay,
Hi,
good.
everyone.
Yeah. No, Professor Wu's lab
Hello.
still working hard. That's why we.
Oh,
Hello.
hi. Oh, Yunji, how's it going with your graduation last week?
It was very good. I take a lot of photos with my family.
Oh, cool.
Oh, yeah. Okay. Graduation. But I saw your graduation in the fall, right? You had 2 times per year.
Uh, Last graduation was my um university, and this is my master degree
Hey.
graduation. Yeah.
Oh,
I mean, so your graduation in your university had 2 times per year. Once in springtime, once in the fall. Because I was in your university, I think I was in August. This all time this had some graduation at that time too. Celebration. It's a ceremony for the graduation was in August.
Yeah, there is also the graduation ceremony in August too. Yeah.
That's that's nice. So you get a what degree you get? You get a master degree or PhD?
Now I got a master degree,
Oh,
and I try PhD.
oh, okay. Congratulations. Congratulations. Excellent.
congratulations.
Yeah, congratulations. Yeah.
Thank you.
Mm-hmm.
Hi, everyone. Hope you have a great week in last week's FVCOM online course. So if you have any questions about uh, the lecture 4 and the lecture 5, especially the non-hydrostatic and the external forcing, feel free to read them up here. Dr. Chen and I will answer them. And before we start, let me first summarize what we have discussed last week. Um,
No, can we access to the my course? So
yes.
discuss about it,
Um,
everyone able to see that.
yeah.
Mhm.
Oh, I'm sorry. Please wait me for 1 second. I log in the wrong account. I cannot share my screen. Sorry for that.
Okay. Oh, sorry. Okay. You mean是 okay, host that not allow the multi-access to share at the time. So what I should do? Wh- What is supposed I should do? Okay. Now you become a host. Okay, good.
Yeah. So sorry for that. I have two accounts, and only my school account allows me to have a 1 hour meeting.
Okay.
So yeah, so last week, although only 3 students joined the discussion, however, I think all the 3 students have raised great questions, and to make sure that all of us can know what we have discussed. So Dr. Chen and I summarize the questions and answers, and I have put them on the discussion board. So to get access to the discussion board, first log in your my course, and then at the middle of the course list, please select the discussion board. Uh,
Mhm.
yeah, and now you can see we have already created different forums for different lectures. And
Okay.
last week, 2 students asked questions about the lecture 3. One is
Mm,
about the integration and the most big scheme, about how to set up the sleep steps and why we need to set that. And the second question about the K epsilon and Malloy model 2.5 model, turbulence model. And if you click one of them,
mhm.
we summarize all the answers here. And I also attached the original question as a picture. So this question is raised by Yongsung Zhang, which is really a great question. So if you are interested, feel free to review them here.
Mhm.
And let me see, there is also another question about the wet-dry setting. So I put it in lecture 6. Although we haven't started, but however, um, uh, uh, Jin Yong Kim raised a question about that, which is also a great question. So the answer has been listed here. So if you are interested, feel free to read it here. And also, if you have any questions, feel free to raise them here, and Dr. Chen and I will answer them as soon as possible. Yeah.
Good. Yeah.
And what's more, let's see. Oh yeah, and also another thing is that we also make a record for our last discussion, and also the discussion today will also be record. And earlier today, I sent out an email with with a web link. Have you all received that?
I have question about that. I received that email, but you said you can find the record in here, and there is no some link or path that I can download or show the video.
Oh, okay. Let me check it. Okay. Wait a second. Let me check on my end. Is it because I put it on the YouTube and I thought it could be get access to all of us, but before that, let me try it. Yeah. So it's this one. Can you see? Oh, this is mine. Yeah. So I will post the link in our chat, and could you please to try it now to see if it is available?
Okay.
Good.
Oh, I can see the video in YouTube. Thank you.
Okay, that's great. Thank you so much.
Okay,
So
good.
after the meeting, I will send the link again to make sure that everyone has a link and get access to our last discussion.
I
Okay.
think Dr. Lee, you do a good job to create each lectures, make it a catalog, so then student people can, list the question in that special section, so then we know where it is. That's good. That's excellent. Okay.
Oh, thank you. Yeah. So that is all from my end. So, Dr. Chen, do you have anything
No,
else to add?
I don't have anything I want to add. I think you do an excellent job. I just ready if you have anyone had a question, so Dr. Lee and I can help to address your questions.
Mhm. Yeah.
Okay.
Yeah. So now it's question time.
Then I want to ask some about the this week lecture.
Okay.
Can I share my screen? Okay.
Yes,
I
please.
okay, thank you.
Hmm.
In this week, the lecture is about the non-hydrostatic option, and um, in the lecture,
Mhm.
the they describe the two methods to calculate the Q, which is the pressure of non-hydrostatic, and I want to know when I should use the pressure correction method to calculate the Q. Is there any example case?
Mhm. So, Dr. Lee, you want me to answer the question, or you can answer the question?
Dr. Chen, would you please answer this?
Okay.
This is a little hard for me.
Okay. So, uh, the four things I like to explain what the difference that's two method is. Okay. They have we call a projection method. One is called pressure correction method. If you look like a equation, we show here, so the Q is no, Q represented non-hydrostatic the pressure. So the n plus 1 means you integrate for next time. Okay, next time step. You start for n time to integrate to get a m plus 1 time. So then you look about the pressure there, you get a no Q par. Q par there, that's the background pressure, but not, sorry, that's just non-hydrostatic, okay, the pressure. So then what happened, so if you was use the A equal to 0 as projection method, that means when you do the calculation, you directly from the n time to calculate non-hydrostatic pressure, that's potential pressure. So you direct the calculation n time to n plus time without the correction from n time. Okay, because now you look about equation, you look about the step 1 equation here, look about the left side equation here. You see, you get a non-hydrostatic pressure. We assume the motion is kind of so diverging free the motion. So you see here is the pressure. You see that's the n time. The pressure gradient is all right side is n time pressure, right? So then you see you use n times the pressure, then you calculate in n plus time momentum equation. N plus, that's the end. You see that start is the kind of called intermediate velocity, but because we get a vertical diffusion, that's why we just calculation intermediate velocity use the n times the pressure. N times pressure. That's the pressure include two parts. That's correction here. If you A equal to 0, A equal to 0, resistance equal to 0,
Yeah.
right? No,
Right.
I forget to put it here, cross side here, okay? I'm missing something. Okay, that's equal to 0. That means when you to n time to integrate for n start time in the mid time, so you don't consider non-hydrostatic pressure. All right? So non-hydrostatic pressure, you correction from here. You see here?
Oh, sorry, I can see your mouse or some
Yeah, a mouse.
point.
You ever see my mouse? No. So then you
Yeah.
look about then you look about you look about step 2, right?
Oh, here.
If you had a step 1, so then you see your pressure, use the end time pressure calculated, like intermediate time. Okay, then if A equal to 1, equal to 1, you consider this kind of n times, but n times that's kind of background pressure, right? N times background pressure, you consider that. But A equal to 0, you don't consider that. But then you just directly you go to the step 2. Step 2, you only consider perturbation, right? Change of the background, change of the non-hydrostatic pressure. So then under pressure, so you just integrate for intermediate time, you don't consider non-hydrostatic pressure, but then you only consider non-hydrostatic pressure contribution momentum equation for n plus 1 was a perturbation for the difference. This is called a projection method, right? For the pressure correction method, that means that when you calculated the n plus 1 time, you include step 1, you consider n times background, n so you include non-hydrostatic pressure at step n, time, right? So you consider this one, but n times still not have a the kind of Q, like a Q par. It's like a difference, perturbation term. That's the changes the pressure. So then your second step, you add the perturbation in. Then you get the m, so velocity was m plus 1. Okay. So what it means is this means, okay, when you calculate it, use a pressure method, this is kind of approximation is the first order. right? Because you don't consider not just the pressure with the end time. You're directly correcting your velocity, the corrected velocity by the difference, by the change of pressure. That's the Q part, right? So this means supposedly your velocity when changing your n not just the pressure, the n time should be contributed to velocity changes. But for projection method, they don't consider that. They run a hydrostatic model first, right? You see, if the Q equal to 1, Q equal to 0 here, they all tends just to have a hydrostatic. In n plus 1 time, so step 1, they only consider hydrostatic contribution to velocity changes. So then they make a correction, right, for the step 2 with the pressure changes, with the change of the nozzle pressure, make a correction for velocity. So that's why the order is a low order. Suppose you should consider, because in the end, your non-hydrostatic pressure already there, right? That's why if you consider, that's why you will be, the two method difference. One method, projection method, is called first order. Numeric accuracy, the pressure correction method, this is get a second order correction, right? So that's why you end time velocity, when you get step 1, you already consider non-hydrostatic pressure contribution to velocity changes. Okay, so then you add another correction in, right? So that's why this is second order. But then the projection method for the first step 1, they don't consider non-hydrostatic pressure because A equal to 0. Right? They assume intermediate velocity at the time was hydrostatic. Then they make a correction, and from the m star, n equal to star to the n plus 1. Right? That's why this is the first order. That's a difference. Your question is which one you should use. Right? You see, when you do the non-hydrostatic model, which one you should use? Well, if you want to get a very better accuracy, you should choose pressure correction method, right? However, if your problem, you don't really care much about the accuracy, when the resolution, when your time step become very small, two methods very close each other. Okay. Okay. Because of this dependent time step. But if you want to get a more accurate results, right? So you should choose A equal to 1, the pressure correction method. Stanford University had a professor called Oliver. He's had a Stanford model called the Centron. He just make correction is called a projection method. Okay, so that's why if you look at the paper, he had a paper published when he ran for Soliton Way. Soliton is the idea like Soliton Way. You run it for 5 seconds, you can see amplitude becomes smaller, damping, because of forced also approximation. Okay, so then if you look about Light's paper, 2010, he also compared with Stanford method. So he found the reason projection method, he get a damping because the sea level, water level condition, sea surface. Okay, because he chose the value of a non-hydrostatic pressure was not in the surface. That's the, in the first layer, in center of the first layer. Okay, if center of first layer, you don't make a pressure correction, so this could be cause damping, could cause sea level changes. So that's why you get a damping solution. Then I use the pressure correction method. Then he found that this solution becomes much better. It's not damping anymore. Okay. So then also I was changing the projection method too. The projection method in the FVCOM is different from projection method with the Stanford model. Because that model just use like a first order approximation and no surface boundary condition in the first layer. But this method here, he put it central, but he make a correction. Okay, he make a correction. He make some interpret correction, so make sure this boundary condition not either between the two layer, between the first layer, he go to get approximation and C surface. Because most time you should give a Q at the C surface, Z equal to zeta, right? But but when if a projection method he put like a Q part condition was in the center of the first layer. That's he not really the surface condition, right? It's the first layer condition. That's why mathematically you can cause the sea level change because perturbation sea level can equal to pressure change can equal to the sea level change, right? So that's why missing something. So after make correction, that's better. Okay. So you can choose. I suggest you choose a pressure correction method. No, right?
Okay, thank you.
That should be better because that's the second order. You also can find a paper, Dr. Light's paper, 2010. His first paper, he described very detailed and what the projection method was the pressure correction method, how this work. He used a soliton, the soliton, wave, see how the simulation. So he compared with a Stanford model. He also compared with Ron's model. Ron had 900 at the time. So both model had just use a projection method, you get some error. Now you show the paper here, yeah, the Dr. Lee give a link, so we can open. Probably you can open the paper and show you where they are. Dr. Lee can open the paper.
I will stop share screen. Okay.
Yeah, I can show the paper. I can describe with you. Okay. So you go to. No. It's not that paper. Not that paper. That's the 2010 for first paper for idea is the 900 started. Yeah. Okay. No. This second. No. This is not this paper. The first paper. That's the part 2. You get a part. Yeah.
Part 1, we check.
Okay. I think line.
This one.
Yeah. Yeah. You look at part 1.
Wait a second.
You see this paper, you go down the soliton way comparison. You see here. My lecture, I give the example too. You see the soliton way comparison, go down. Yeah, go down here. You see that's picture. You see that's the soliton way he propagation. So you can see the velocity not damped. Right? You can see the sea level was really match soliton way. Right? Then you can see another method. You can see he coded for another method. Okay. Do you have another? Do we go to figures? No, that's not one. Go to 6. Do we have 6 one? Probably he not include because he don't want to mention. He don't want to know. Okay, probably not. He didn't include that's figure. You see that's
Okay.
figure? No, that's figure. Yeah, that's figure. You see here? That's figure. You see now it's the model is the analytical solution you do here. You see there's a computation that analytical solution divided the surface elevation with the model under pressure correction method for surface standing wave. Okay, you look at analytical solution, saw the line, computed the solution, now the static, Q equal to 1 the surface, dash line, Q is 1, compute the Q equal to 1, and the top sphere. You see the top sphere? If you put only like a Stanford model, he didn't include Stanford model there because he don't want to make people feel unhappy, right? But then he just make because Stanford model just use a Q equal to 1, Q equal to 0 at the top sphere. So light was changing the Q equal to 0 at the sea surface, right? So then you see the dashed line. That's you get a phase shifting, you get a damping. If you Q equal to 0 at the surface, really match very well. But if you do the Q equal to 1 and the top shear just, so then you see they get after you see at the beginning to 15 minutes, everything okay. But after go to 100 or 500, you see here, shifting, also damp. Right? That's the Stanford model show that. It's the wrong model show that. Right? So he mentioned he didn't want to make people unhappy, right? But he just mentioned, okay, if you use this boundary condition, that's the problem you have. Okay, that's the Stanford model. Ron's model just uses that's kind of competition condition and the Q equal to 0 at the top shear. That's what I mentioned before. Okay, now you understand?
Yeah, I understand. And I searched that paper after the class. Thank you.
Okay, good.
One thing I want to mention is that in FVCOM, the name list, you try to set the select the method, either projection or the pressure correction. There is a switch called proja underlying switch in the name list non-hydrostatic part. So for this switch, it is a little different from the factor that in the coding. So in the coding, when we set A equals to 0, so it is projection. But however, in the name list, in order to use a projection method, so you need to set this setting as a very large number as it listed here. So for example, you may just set 9 billion, so set some big number to make sure that in your case, your integrated time step number is smaller than this proja switch. So if you want to use the second method, A equals to 1, which is a pressure correction. So as it's shown here, just set is -1 or -2, which is a small number. So it will set A equals to 1.
Yeah. Okay. Yeah, that's why the equation and when you're coding is different. Sometimes coding they have to, because you put a 0, sometimes it come out not very good, right? Because that's why they put a number there. Okay, but you have to read the manual. You just understand what is different, the projection method and the pressure correction method. So now you know the difference. When next time you use you can choose what you want. But projection method is much stable. But he got a shifting, but it's not much shifting because the light was corrected. He put a Q equal to 0 at the sea surface. That's why he didn't find a damp, even the projection method. Okay, the key issue because the projection method is a first order approximation because they put a Q equal to 0 in the top shear. Okay, once you put a surface, but put surface is not easy. Put surface is not easy, okay? Live will do a lot of method to how to put, when I see this very simple, but he had to do a lot of coding, make sure the Q can be specified at the surface. Q equals 0, okay?
Okay,
Good,
thank you.
okay.
Yeah, so I put the reference and its download link in the chat section. So if you are interested, please see the see last paper. So any other question?
No, if you don't have, we had most of 1 o'clock, right? Oh no, we still have a half hour, right?
Yeah, we
We
have
start
they have.
8:30. I thought we started at 8 o'clock. Sorry about that. Okay, and other question?
Professor, I have a question with the non-hydrostatic model.
Okay.
So I show the windows. So do you see that?
Yeah.
So my question is here, you showed the slide 2. you show the equation with hydrostatic equation in left and non-hydrostatic equation to right. So the first term of each equation is U vector equation, and second is V vector, and two equation is completely same. So my question is that if the non-hydrostatic equation, when it vertically means it is same for the hydrostatic equation.
Sure, sorry. So, yeah, you raised a good question. Let me explain to you. You look about two equation horizontals is exactly same, but however, P, the pressure definition different. Okay, you look at the left side, the P is the pressure, and also right side equation after the P is also is a, if we use a capital P represent the pressure. So then you look at the two equations, it's all that's the equation exactly the same. But however, there's a pressure definition different. For the right side term, the P equal to pH. Because you see,
Yeah.
you see this low here, P equal to PA atmosphere plus, okay, pH, right?
Yeah.
Okay, so this one is atmosphere, one is pressure here, okay? But here, the right side of P equal to PA plus pH plus Q. That's different, okay?
So you means that
Yeah,
the equation
yeah,
form is same,
yeah.
but
Equation forms the same, but however, the P in both equation definition different.
I understand
Okay,
that.
now
Yeah.
you understand. Now you understand because Q, because in the right side equation, the P don't include the Q, not just the pressure, but the right side equation P include Q. So I just want to be, reason I want to write this way, I just want to show you, you look at equation same, one only difference is, right side equation, so your P include hydrostatic, also air pressure, also include non-hydrostatic pressure. But right side term, you have, air pressure, then you get a hydrostatic pressure, but you don't consider non-hydrostatic pressure. Okay, that's why this equation different. So also it's a good thing to do that. The reason you do this way, you can see, you can separate it, right? You can have a hydrostatic component. You can another as another component.
Then I have another question. So you showed that definition P is different to hydrostatic and non-hydrostatic.
Yeah,
So if the Q is zero, case is same for non-hydrostatic and hydrostatic.
yeah. If the Q equal to 0,
Yeah.
okay, Q equal to 0. So then you see the hydrostatic now that should be same. However, in the vertical still not same. You look at the Q equal to 0 here, right?
Yeah.
The Q equal to 0 here. So there's a horizontal equation, go back to hydrostatic. But however, vertical equation, if you hydrostatic, you cannot write this term. You get a acceleration vertically. You also have another pressure. You also have vertical diffusion. Vertical diffusion term here. But hydrostatic is a balance. But the pressure and the buoyancy for the pressure then balanced by the gravity force, right? But then if you see that's the vertical equation hydrostatic, non-hydrostatic include W vertical average, vertical velocity acceleration, you get another pressure, you also include diffusion, also have a horizontal diffusion too, right? So you have to take a, they turn out, they turn out, they turn out, you see here, okay? So then you can get, this kind of pressure grading. Okay, because in the non-hydrostatic model over here, because these two terms get 0, so hydrostatic can get a balance. So non-hydrostatic model don't include this balance because it get a 0. That's why you only have the non-hydrostatic Q plot here. Okay, right?
Okay, I understand that.
Are
Thank
you
you.
understand right now? Yeah. That's why you look at Horizontal equation is similar, but definition different. But most, most important thing now is that first thing, horizontal velocity, pressure, now just the pressure can directly cause the change in horizontal velocity. The secondary, then now just start the motion, you get a convection. The vertical velocity. So vertical velocity, the vertical movement velocity, not caused by converging, diverging. Right? He's caused directed by the forcing, by vertical gradient for not just the pressure. But however, you still need to be satisfied by the converging, diverging. Called an incomplex equation. In hydrostatic model, your vertical velocity not caused by the forcing, not a force, not like a actual forcing to cause the water movement vertically. The water movement vertically really based on a horizontal converging, diverging. Okay, right?
Okay.
So then the non-hydrostatic model, the vertical movement is not caused by the converging, diverging. It's directly caused by forcing, but it satisfies converging, diverging. Okay, so I can use like a pen. Do we have a pen here? I don't
Yes,
know. No.
it should be on the left side.
Okay, write the ball. I can use the write ball here.
Mhm.
I can show you something. Okay, you can see for the hydrostatic model, you get a partial U.
Dr. Chen. Oh, yes, I can see. Yes.
No, to everyone able to see that?
Yeah, I
Yeah,
can
we
see
can
that.
see that.
You can see that. You
Yeah,
the
we can see that.
hydrostatic model, you get this one. W. That's called incomplex equation equal to 0. Right? So in the hydrostatic model, so this your W velocity really caused by the converging, diverging, by the horizontal motion. Because you have no forcing can cause the vertical motion except the converging, diverging. But the non-hydrostatic model, you are vertical velocity, du dt, I just want to write simple, dw dt was proportion to your gradient for non-hydrostatic pressure. This causes the water changes, W changes. Hydrostatic model don't have that. Hydrostatic model get this two-term balance, right? So then after you get this W happen, but this W still need to satisfy for this equation. Okay, so motion caused by the forcing, but however, after motion was happen, you still need to satisfy the incomplex equation. But in the hydrostatic model, okay, vertical velocity only caused by converging, diverging. They don't have a forcing cause that. They only cause like a, the Warren conservation. Okay. Now you understand?
Yeah, I understand.
Okay, I clear this one. I don't want to make it a problem. Okay.
So, Dr. Chen, I have a question. So in the do you mean in a non-hydrostatic method, the water parcel is still incompressible, right?
Yeah.
Okay.
Both hydrostatic and non-hydrostatic model, both water satisfy the incomplexity, assumption. Only difference, hydrostatic model, the vertical velocity direct caused by converging, diverging with horizontal motion. Okay, but now just the model, he was the velocity, that's the vertical velocity established changes due to by the forcing. The forcing. But after this vertical velocity happen, they still need to satisfy it's kind of no diverging free, right? Just like a incomplexity for the condition, right? So, but just they both no, but but the difference is just that's the reason, and that's the reason hydrostatic model, they're not able to resolve the convection. For example, you have water is a cold surface, deep is warm water, then because the water is heavy, while in the surface, no lighter in the deep region, they get quickly overturning. But a hydrostatic model, you see, there's 2 times balance. That's 2 times. That's 2 times balance.
Which
Right.
two?
That is the vertical pressure gradient balance was gradient forcing. That means even the water unstable, they're not able to overturn it. Okay, they're not able to overturn it because they always buoyancy forcing, always balanced by the weight, the gravity forcing. So for example, you put a parcel there, the parcels you put it like a 10 meter, the parcel always stays at 10 meter. The parcel only can move from 10 meters to other depths is with the converging diverging. All right, but a non-hydrostatic model. So if you heavy water was in the, for example, 10 meter is a cold water. So because the pressure, pressure turn, right? Non-hydrostatic pressure turn can cause the force motion directly go down. So that's why you get a convection. That's a different physical mechanism.
So when to choose, when to use the hydrostatic and when to
That's a very good question.
not to use.
Depends on the scale. If you want to resolve convection, you must, if you want a non-hydrostatic model was very important because your vertical resolution, your vertical depth should be, the vertical depth, and the horizontal depth should be on the same order. Okay, for example, you go to the 1,000-meter depth, right? So you can use your model as the 1 kilometer. You can resolve convection, non-hydrostatic, because your vertical depth is 1,000 meters, your horizontal resolution is 1,000 meters, right? However, if you go to shallow region, you have a water depth only 100 meters. But then you use your model resolution 1 kilometer. Even you turn on the non-hydrostatic will not affect it. This turns very small, right? So then if you want to resolve the non-hydrostatic in that region, you have to make your model resolution at least 100 meters. Your resolution must be, horizontal resolution must equal to your vertical resolution, okay, vertical depth. Then you can resolve the non-hydrostatic. If you look at Dr. Lee's paper, he ran for non-hydrostatic model, LC couple model. LC couple non-hydrostatic model for the storm, for the big hurricane. All right. So he had a resolution 1 kilometer resolution. So his model showed very clearly convection was in the deep ocean. Because he's 1 kilometer resolution, that's why he showed a convection in the deep ocean responds very strongly by a non-hydrostatic event. But when they go to shallow water, his resolution is 1 kilometer resolution, but non-hydrostatic condition required horizontal scale and vertical scales in same order. But he did not show very clearly non-hydrostatic event. He only get a first order correction, but not a truly non-hydrostatic event come up. Right? See, if he want to resolve, he had to reduce resolution about 100 meters. Okay. That's the reason, not the model, you have to be, what time you need to resolve it, you really dependent on your, the physical scale and numerical scale must match. Okay.
Thank you.
Do I answer your question?
Yeah.
Okay, good.
Thank you.
Yeah. Now Lee has put his paper online and show you. You can read his paper. Really interesting paper. That's the first paper talk about non-hydrostatic model for hurricane study. So clear confusing for the people confusing people have. But you put a non-hazardous model, oh, he said, I run a non-hazardous model, I already had a fully coupled model, but they don't know. You know, you have to have a certain resolution, you can really resolve convection event.
Mm.
Okay. Yeah.
Yeah, I have listed the paper that Dr. Chen mentioned in the chat section. It is a paper in 2022. If you are interested, feel free to download it. Any other question?
Do I address your question soon?
Me?
No, I mean another, you know, who's that?
Gmail sale.
Jing Miu, right? Jing,
아,
뭐,
지명서.
Jing Yong. Okay.
Yeah, me.
Yeah, yeah. You ask now the question. I just ask you, do I address your question?
Oh, no, I have no question anymore.
Yeah, okay. I'm just means like the student asked me question for now just a model equation. So Su, right? You know, called how to pronounce your name? Called Ji Ming Ji Yong Su.
이명.
Jin Miao. Okay. Jin Miao.
Yeah.
Jin Miao. Okay. Jin Miao. Okay. Sorry.
Thank you. Okay, thank you.
Okay.
It is too difficult to foreigner.
No,
Not
we are.
Korean.
It's fine. It's fine. I think.
Actually,
Yeah. I think Yong Ji Song. That's easy to pronounce.
actually today I went to Ki Huan's office and asked Ki Huan about how to pronounce the three names of the student of the last week discussion, and Ki Huan taught me how to pronounce.
Yeah. I need to learn. I need to learn. Okay. You know.
Yeah. So any other question about the non-hydrostatic or the external forcing?
Professor, I have a question, but it is not related to the class content. But it's a technical question
Okay.
about compile. Would it be okay if I ask?
No, it's okay. Any
Yes,
question?
please.
Okay.
Yeah, you don't need to all ask a question about the lecture. You can ask any question. You know, when you use FVCOM, you have. Okay. So that is a good time for people presenting the question. So we try to help you to address your question. Try to, you know, try to help you out. Okay.
Mm. Can you see it?
Yeah.
Mm-hmm.
Okay.
Okay. That was in the make inquiry, right?
Yeah. During the compile of FVCOM 4.4.7 with the passive library, T-convert error is occurs and the Julian library fails to compile. Is this a known issue? If so, how can it be resolved?
Okay.
So your
do you install it for Julian software?
Yeah, library of Julian. Yeah.
Library, yeah. Yeah. No, this is a question. Pretty sure Siqi can answer. Okay.
Yeah. So on the I first I want to double check. So on the right side it is an error message, right?
Yes.
Yeah.
So I don't think this is related to the PET-C library. I think this should be some error related to the Julian library, as Dr. Chen mentioned. So based on the error message, I think there are several potential reasons. So maybe first it is because you use a different version of Fortran compiler to compile the Julian library with your FVCOM compiler. So when the users try to compile FVCOM and the Julian library, please make sure to compile both of them with the same Fortune compiler, especially for the same Fortune brand and the same Fortune version. For example, if you use the Intel Fortune, please use Intel Fortune for both of them. So I don't think this one is related to the Pepsi.
Look like arrow is a call. He said, you know, it look like a make it include file. He said arrow come from the module was the Julian. Right.
Yeah. So
Yeah.
I suggest you to recompile the library Julian. So after the Julian is compiled, there should be a lib julian.a created, maybe also a T convert, but in FVCOM we do not need to use a T convert, but just to make sure if whether these two files have been created. So if these two files is created, so supposedly your compilation should be fine and you can go for the next step. If you still have any question, please feel free to email me. I think this should be easy to solve. Don't worry about that.
Yeah. Okay. Good.
The reason I suspect that the issue is related with PESI is that the problem does not occur when I off the PESI module.
Okay.
Yeah. So, you know, sometimes you look like a Pepsi, come the problem, probably not a Pepsi. Look like this one, look like a Julian library cause a problem first. So then the Pepsi not working. Okay. Yeah. But you try, see what's happen. If you still have a question, you can send an email to the Dr. Lee, okay?
Okay.
Yeah.
Okay, thank you.
Other question?
Oh, Professor, I have a question. Can I share my screen?
Yeah, definitely. So your name is easy to pronounce, Mingwu Park, right?
Yes. Mm,
No, I had a classmate when the MIT called Park 2. You know, he after graduate, he went back to Korea. You know, he was in the Cody, you know, institution working there. Now the Cody name was changed another name, right? He moved to Busan. Okay. Oh, good. Okay.
Oh.
Yeah.
Okay. In terrain following coordinate, the steep bathymetry gradient can cause numerical error, as shown in this figure. I studied that in non-hydrostatic model, by reducing the time step, we can decrease vertical velocity and thereby reduce numerical error. The same error occur in hydrostatic model as well. In hydrostatic model, what method can be used to reduce numerical error that occur in the steep bathymetry gradients?
Okay. You know, for hydrostatic model, reduce error, best way to reduce error, make a parental resolution is, you know, make a resolution high. Okay. No, increased resolution is really the method to solve the sigma error. Okay, resolution. Okay. So you make a resolution, the particular slope region, you make a resolution, high resolution, the sigma error can be reduced. That's significantly, you know, when, you know, so this time step, that's the issue. And, but also horizontal resolution, that's critical. You know, you need to make a horizontal resolution very high, so then you can get a better result. No, we recently we testing the sigma error, right? For the idealized case, we can make it steep, very steep. The before, like if you look like a wrong model, so they make assumption if the slope larger than 0.02, they have to do the smoothing. The coding have a program automatic smoothing for you. Okay, they just smooth topography, make sure the all slope not larger than 0.02. But then our FVCOM don't need to do smoothing. We can do that. But then a lot of people report, say FVCOM had some kind of sigma error when the bottom part is very steep. So recently we are testing, method use the new coding. Also, probably I think that before has some bug some there. After we fix new coding, we testing. We even can put the steep topography 0.1. No, we still running the beautiful like a slope. We put a seven. We put like a lake, circulating lake. We put a topography, linear topography. We put the topography very steep. Also had a one glacier crosses from 0 to 500 meter, very steep. So then we run a model. We still see very beautiful surface Ackermann layer. We put a wind driving. Also, we can bottom Ackermann layer come out. Okay, so then we found, so we have been through testing. Recently, we have been put like a vertical advection turn in the diffusion turn equation solved in plate scheme. So we found that this model becomes more stable, but also get the same results, like stratification. So then, but for hydrostatic model, the best solution to reduce sigma error just make a horizontal resolution small, no, horizontal resolution high resolution, glacier smaller. Okay, that's the reason you look at our model for our paper publication, most on the slope region, so we make the resolution very high, right? Make a resolution very high, the slope region. That's the reason we do that. We just want to make sure you can reduce sigma error. But you look about you should not only worry about sigma error, you also worry about the topography can cause like eddy. Because when you go to steep topography, because for example, the slope region, you get a lot of canny, right? Canny like a just go like this way, okay? The canny. So if you don't have much resolution without the canny, so then the flow go to the canny location, it could cause the eddy. But if the resolution not high enough, the eddy can big. Propagation very fast because you don't resolve, right? But when you make a resolution high, you see the eddy can traffic in the candy. That means your resolution is sufficient enough. Okay. Solution is reduce the horizontal resolution. Vertical not very matter, but horizontal resolution is very critical. But Dr. Lee's paper show if you lose non-hydrostatic model because of convection, right? If your resolution is strong, high enough, slope region. So for example, hydrostatic model, he didn't show this kind of bigger convection over there, right? So but now you turn the non-hydrostatic, you get a big convection. The reason because you get a non-hydrostatic model, so the convection process is a very small time step. They're very fast. Just like a wave, for example, gravity wave propagation very fast. You have a very small time step, you can resolve the gravity wave, right? But same way you have a convection. So the convection is really fast. They go to really quickly, convection, the cooling water come here. If you don't have a small time step, right? So you can overestimate this convection. Now, for example, the cold water, they come to, for example, they're moving for example, 1 minute to 1 meter for 1 second. But your time step is larger. You suppose they go to the 2 meter depth, you go to 5 meter. That's the reason they get a big overturning. These people talk about the overturning issue, not a sigma error. Okay, because in the hydrostatic, before he turned on the hydrostatic model, he turned on the hydrostatic model, sigma error very small, no sigma error, no convection. But this one just, if you're not hydrostatic, you get a convection. You see if time step is larger, so you do have this kind of big convection happen. When your time step is smaller, reach to the convection scale, then you see that this is no convection happen. Right? That's reasonable. That's another issue. It's not sigma error. It's called how to resolve the convection, vertical convection issue. If your time step is too larger, you probably overestimate the convection, vertical convection. So when the time step go to 2 seconds, you see that you don't see the much convection anymore. right? You get a very beautiful stratification come out, right? Because your scale send your time step will send your natural set as time step. Okay, that's why you need to test the model. See that no, a lot of the model right now, they keep running the model. Show my model very stable, but stable model doesn't mean you produce the right physicals. Right? The Dr. Lee's paper just show you need to have a right time step result, right physical. You have to test your model. Right? Because you know he don't put a cooling there, supposedly no convection. But however, but the vertical resolution time step too big, you can cause artificial convection. That's the A picture show that. Okay, so then now we call it converging study. Have you heard of converging study? If a numerical converging study means you have to have a numerical time step, numerical time resolution time step, also numerical horizontal resolution, same as your physicals. Your numerical scale, time scale, what no special scale must be same as your physical scale. The physical scale, then you get the correct answer. If you don't do that, now this model can cause artificial convection. Okay. I answer the question?
I have no question anymore. I understand. Thank you
Yeah.
so much.
Good, excellent. Now we pass the time. That's good. You good, very good question. Okay.
Yes. Thank
Okay.
you.
Yeah, so now it's already 1 hour past. Thank you so much for joining this discussion. I think our discussion is really good. Students are asked really great questions. I will also summarize all the questions at the last week and post them on the discussion board. And also, if you have any questions, feel free to read them up and all the students and we can discuss them together and learn together. And thank you so much for joining this meeting. Let's see us together next week the same time. And have a good day.
Oh, sorry, I have some questions.
Oh, okay. Yeah.
Oh,
Mhm,
okay, I share my screen.
mhm.
Okay, can you see?
Yes.
Actually, like last week, this question is also not really related to this week's lecture, but when I was an undergraduate student, I tried to apply FVCOM to the Mariana Islands in Western Pacific. The most challenging part was dealing with this bathymetry. As you can see here, Guam was only 50 kilometers away from the Mariana Trench, so I wanted to ignore this trench, but I was concerned about ignoring the Mariana Ridge's influence in this area because that would make the gap between the open boundary and the islands too small. So I assume there was no flow, no current below 3,000 meters depths, and I just set the maximum depth, so 3,000 meters for my whole domain, keeping the arc in it. So my question is, what problems could arise when applying these bathymetry conditions directly to the FECOM? And second is, what criteria can be used to determine if I can ignore the seawater below by applying a level of no motion?
Okay, let me address your question. First question, we tested this problem, same problem like you did in the South China Sea. Okay, South China Sea had one region very shallow, had a ridge. The ridge, the depth there is most deep than 10,000 meters. So that's, like a small channel over there. So then if we keep the whole, 1011, more than a 1,000 meter depth there, so we had to make it a very high, very small time step because they get a lot of internal wave. They got a lot of internal wave come out. So you had to have a very small resolution about there. You also need to be horizontal resolution very high, also time step very high, very, very small. So then you can run the model stably. But then your whole domain calculation will slow down because of that. So if you only nesting the model, you only run the model for nesting domain, not the whole domain, only for here, you can make a resolution really high. You don't need a cutoff. Okay, you don't need a cut like a 3,000 meter. So then you can get the model running stable. If you only run because if you run a big model, you're probably not able to pay off. But if local model, you can do that. But then you have to very small time step also make sure it's a very small, like a very small cell along the island. Okay, you only run that. That's you can do that. Okay. But then for you see that because you found no motion in the deep region, you cut off 300 meter, 3,000 meter. That's really dependent on, because you're very hard to see the deep ocean no motion, right? You cannot define how is so 300,000 meter or 4,000 meter, but a lot of region the velocity is weak definitely, right? In the deep region, you see a lot of people saw the deep ocean no motion before, but now they have a lot of observations show that. So they do have a current happen in that region, but it's smaller. Okay, so that's why. So if my suggestion, if you run only nesting model, you should include all the really depths. Right? If you know, depending on what you want to do. If you only care about a near surface current, how the change for the up layer, for the island, for the ridge. So you can cut the 3,000 meters, no problem. Because the water velocity there is very smaller, right? You don't really care. You don't want to look at this circulation down. You can cut off. 3,000 meter and 4,000 meters, that's reasonable, right? So then you take advantage for that. Your resolution don't need very high. You can run the model. Right? So they don't have a criterion say the velocity, no motion velocity, because you don't have observation data. So most time, depend on what type of circulation you're looking for. If you're looking for the wind driving circulation, the most about 1,000 meter above. Wind driving, right? So if you look at like some deep ocean circulation, like a submarine, like a buoyancy driving circulation, they can go to the deep region, very deep, like 10,000 meters. So really depend on what question you want to address. If you're only interested about the circulation, wind driving circulation, or tidal movement around the edge, you don't care about the high frequency internal wave, for example, right? So you can cut the 3,000 meters, no any problem. Because below this one, most of the region below this velocity very weak, only 2 or 3 centimeters per second. Now you can do that, but no criteria. Okay, just depend on what criterion is, what you want to looking for. Okay, you want to look in wind driving circulation or want to look at deep ocean circulation. If you want to look at deep ocean circulation around the edge, you do need to include all the topography. But if you look about a wind driving only, you don't need. You can cut 3,000 meters. Okay, understand?
Yeah, I see. Thank you for explaining.
Yeah.
Thank you so much, Dr. Chen. Is there any other question?
If you have a question, we can leave it next week. Okay.
Yeah. So if there is any no other questions, so let's end it up here. And thank you so much for joining this discussion, and see you next week. Bye-bye.
Thank you.
Thank
Thank you.
you.
Thank you.
Thank you.